morning. Thank you for coming to the EE Colloquium today. It's my pleasure to introduce Professor Subir Biswas. Subir got his PhD from the University of Cambridge, the one in England, and subsequently moved here. Much of his career has been with industrial research labs. He was first with AT&T labs in Cambridge and subsequently here at NEC in Princeton, New Jersey for a while, as well as Telium Labs. He's then moved to academia to Michigan State, where he's been first an associate and now a full professor for about 10 years, I guess. Today, he'll be his interests largely span a wide range of computer engineering topics, including embedded systems and networks. And today, he'll be talking about a topic I guess will be of interest to a lot of you, which is as users of social media, notably Facebook and Twitter. He's going to look at architectural and resource allocation issues underlying such social media networks. And he will focus on resource trading in such networks, which are enabled by short-range communication, such as near-field. So welcome, Subir.
Thank you. Thank you, Shamik. Thanks a lot. So this work was an outcome of the PhD work that was done with my student, Mahmoud Tagizadeh. So he finished his PhD last year and is working for Google now. And also I must acknowledge that this is partially funded by National Science Foundation and also part of the work that kind of evolved into some social sensing and human-computer interaction type of work that was funded by National Institute of Health and NASA. So I will talk about maybe a couple of slides on the general social network that we guys are familiar with, and then I'm going to make a distinction between that and the social wireless network that we are talking about primarily during this talk. So there is not really much to talk about the social network because you guys are all probably very active, and number-wise, it's almost 1 in 6 people on the planet are registered in one social network or the other. So the penetration is really is really high and also going up in a quite rapid rate, right? Now, one of the underlying ideas that people use in social network is the communities, right? And if you notice that most of the sort of money-making ideas and the commercial ideas in terms of advertisement and so on, they heavily rely on this thing called virtual community within a social network, right? So this particular diagram essentially shows my LinkedIn profile. So there is a tool using this, you can create the network. So I'll just make a couple of comments here. So see, the center is obviously myself, and then it creates connectivity between myself and all my contacts on LinkedIn, right? So the thing to be noticed that you see that there is this clustering that is pretty obvious. These are sort of virtual communities that are being formed, right? So I have communities from my grad school, not so strong as the other ones. So for example, my last couple of jobs, so there is one here, and this is the sort of MSU IEEE type of community, and then this was my Telium community, and then there is NEC communities here, and grad school is here. Now, so the idea is that you have these different virtual communities that are being formed, right? And those communities are also to some extent overlapping, right? So you can see that connections between these different communities. So one of the things that the Facebooks and all these media companies they're trying to do, social networking companies, is that try to mine the data on the community and then based on that try to push content so that they accomplish what they're trying to accomplish. So maximum penetration, maximum reachability, and the targeted ads and all these things, right? So the take-home message from this slide is these virtual communities that you see in the social networks that you are registered with, right? So what is the role of mobile devices? Now, this is much talk about this statistic, so I'll just concentrate on this inflection point here. The idea is that over the years, the number of mobile devices through which internet is being accessed essentially already has passed the number of fixed devices, which are netbook computers and your desktop PC and so on. So the idea is that mobiles are being used more and more for your access of the internet, right, and the social network things. Now, the idea here is that as these mobile devices are being used more and more to access the social networks, there is also something that is happening is that you have a physical social network that is being formed, right? So that is what is being termed in the literature as social wireless network, also sometimes being termed as social mobile network. But the key idea now is that as opposed to having a virtual network, right, you actually have a physical social network in the sense that depending on what are the places that you go, and if you carry a device that has near field communication like Bluetooth and so on, and if these devices can discover each other, then they can form communities, and these communities are not on the virtual world, but more on the physical world, meaning there is a physical proximity among the community members and so on, right? So there are two primary differences between this kind of social network, wireless network, and the virtual network like Facebook and Twitter, is that first of all, the communities, as I mentioned, communities are formed based on physical location, right? So you will see that that has some direct implications in terms of how content could be delivered in such a network. And the second thing is also kind of interesting is that what is known as explicit user action, okay? So explicit user action meaning that in order for you to be part of a virtual community in Facebook, right, you have to log on to Facebook, or you have to go to Twitter to follow someone or post something, right? Whereas in a network like, and that's how you become part of a community. But in a network such as this one, right, you don't have to do any explicit action per se. And the fact that every day, let's say you're going to a cafeteria, or you're going, let's say 2 days a week or 3 days a week, and your device is being able to see other devices in the vicinity, that is implicitly creating this relationship in the communities, in the physical communities, right? So these are the primary two differences that you will see can be leveraged in the way you want to make use of this community formation, okay? Now, obviously, there is going to be locality in interaction, right? So in the sense that, it's not completely random mobility that you will encounter between these devices, right? I mean, depending on what place you go for eating and where you live and which classes you take, what sports club you go to play your tennis or squash, whatever, right? All these things are going to be contributing to your community formation and which communities you belong to and how these communities interact among each other, right? So we are going to try to look into this a little bit more formally later in terms of building a model. But the idea is that there is going to be some level of locality in the human interaction and mobilities, right? So there are a number of applications that you can build, and these applications, some of them already are happening and some of them are being perceived. There are startups that are out there which are trying to build these peer-to-peer applications. So the key idea is that if you have a society, and let's say this particular example, it shows the cross-section of, let's say, a typical downtown area. So you have all sorts of different people that are moving around, and there is some locality in terms of who is coming, who is going, and who is staying, and who is seeing whom in which days of the week, and so on. Using that, now think about it, that each of these guys are carrying a mobile device, right? So this could be either your phone, it could be a tablet, but it could also be what is known as these things, right? So for example, this is my digital pedometer that I carry pretty much 24/7, and now this has a lateral link, Bluetooth link, and anytime it finds a device that it already has relationship with, for example, my PC or my iPhone, it uploads the data to a server, and also if I set any specific thresholds in the server, that gets downloaded to this device. So it really does not have a so-called vertical link to go to the network, but using this opportunistic lateral links, what we call, it exchanges information pretty much all the time, right? So the idea is that you have these mobile devices and this kind of devices that are mobile phones and this kind of devices that are sort of implicitly embedded into this society. And the idea is that using that, what kind of applications that you can build. So obviously, this is probably, you have seen this kind of examples a lot. So I'll quickly go by this. So you can have peer-to-peer advertisement dissemination of different types, right? Or you can also build location-based applications. These are the things also have been talked much about, right? You could build a participatory sensing network using peer-to-peer lateral links, right? Or also, you can look into some media-related applications. So for example, depending on the right authentication and the friendship, you can share your Netflix queue, for example, movie queue and things of that nature, right? So all these peer-to-peer applications can potentially be enabled using a peer-to-peer network. And the idea that we are going to look into is that if you can detect that when is the right community is being formed and which of the communities is being formed, how do you manage resources around that peer-to-peer network? So that is really the sort of key idea of the direction that we have started thinking about, okay? So the next thing I'm going to talk about, which is sharing versus trading, right? So we use the word resource trading. So what do we mean by trading as opposed to sharing? So see, sharing, so if you think about resource in such a network, right? So what is happening is that each node, depending on what specific hardware and software capabilities that node has, you can think about it as a resource library, right? That these are the different types of resources that you have. You have your connectivity resources, which is vertical links like 3G, 4G, or you have lateral links depending on what kind of near field communication that you can do. Obviously, you have CPU storage, and also you have an array of different types of sensors and software apps that you have available on the device, right? So the idea is that each device you can think about it as a resource pool, right? The next thing that comes into mind that if you have such a resource pool, right, then you can have those resources being shared across the network, right? So what kind of resources? So the one that you probably already have used, this is this tethering business, right? That if you have a phone, this guy has limited data on his or her plan, right? And these days, data plan is most of the times limited, right? If you have AT&T and so on. So the idea is that if this particular node has unused data, then that data can be shared by, that part of the data plan can be shared by other nodes in the network, provided you have the right protocols and the right mechanisms that are enabled into the system, right? So this is one form of sharing. So we are talking about this bandwidth sharing, right? You can also have sharing of sensing. So for example, let's say that the most recent phone that came out that has a specific type of sensor. Let's say it can sense the air quality in the room, right? Most of the existing phones probably don't have that yet. So then you could actually provide a service. This phone can provide a service with the right middleware and so on, so that other nodes can run an app and measure that what is the quality of the air in this room without having that particular sensor, right? So the idea then is that you are sharing the sensing capability of this node across the nodes into your network, right? So similar other examples, you can have a GPS node. You can have one node that has a GPS capability, and let's say that node is outside the room. Now, inside you cannot have GPS, but you still want to look your location. Then that node can export the GPS service, and the nodes in the social wireless network, they can essentially get the GPS information, and from that it can estimate that what is the current location. So that's one example. The other example could be also that content. So which is what is going to be the main topic of this talk. That the content like your iTunes songs and books chapters for Amazon and apps and so on, this thing, when a particular copy comes to the social wireless network from the server through the vertical link, then that can be shared also across within the network, right? So this is also another form of sharing, which is content sharing. So this kind of gives you some ideas or the spectrum that what are the different types of resources that might be, it might be gainful to share within a wireless network, or what you call a social wireless network. So now the question really is, does sharing work? So here is what I'm going to be putting the skeptic hat of mine, which is that this Manet research, right? I mean, we all have been doing for 15 years or so, but have you ever seen a real Manet that is working, a public Manet that is working, right? And I haven't seen one. So there are Manet, which are private Manet, that has been used by DODs, and they actually have been using that even before the academic community have started that research, right? So the reason why the Manet doesn't work, among many, the most important one is that the energy, right? That if I have to charge my phone every day, why would I let a lateral link to pass through my phone when I really don't have any interest in terms of the data that is going through my phone, right? So that is essentially what it means, is that we are relying, if we are to say that the Manet will work, we are really relying on this energy altruism, what I call, right? That people are going to lend their energy without having any direct benefit. Now, we might argue that this may or may not work, but I would say it's not likely to work. And if you look at the evidence, after so many years of research, it has not really shown indications that it's going to work, right? So then we say, okay, so what you do instead, you try to make it more like a market-driven kind of an arrangement. You say that every time I share something, right, it could be bandwidth, it could be content, or whatnot, I'll get a credit, right? Somebody's going to give me a credit, and that credit I can use to redeem for something in future, okay? So this is what is really the crux of this concept, what we call is resource trading. So we say that, I belong to certain communities within my social wireless network, right? And then I do help people out in terms of giving resources that I have but they don't. But in return, I'm always getting a credit, which is a token for me to get something back in future whenever the time is right and whenever I need something specific, right? So this is really the idea. We say that if we can create a market-driven sort of setting in which this kind of rebates and credits that can be given to make things work. Okay. So there are different types of trading that can happen. The one that I'm going to concentrate in today's talk is the content ecosystem. So content ecosystem, think about this, your app for your phone, right, or the Amazon books, right, or Barnes & Noble books and all these things. So these guys are the content service providers. So these are the three different stakeholders of this system. So the content service provider is providing you content in return of a price per content, right? So when you get a Amazon Kindle book, you pay whatever the price for the book, right? Okay. Now, the second one is the CSP, what we call communication service provider. So that is the one which is delivering the content. So in this case, let's say for Amazon's case, used to be exclusively Sprint, now both Sprint and AT&T. They take responsibility of delivering the content to your Kindle client or Kindle machine, right? So that is the second one, and they get paid for whichever arrangement they have with Amazon, but at the end of the day, they get paid for the delivery service that they provide. And then the final one is the consumers like you and me. So this is the Kindle client in this particular example, right? Or an iPhone which gets the app. So this guy essentially gets the content from the service provider. Now, so these are the three stakeholders, but there could be all sorts of different ways you can actually set the pricing policies so that who pays whom, that depends on what kind of policy that you incorporate. So the ones that I'm going to talk about is, let's say, the Amazon's Kindle model. So right now, the way it works is that if you have a Kindle client, right, again, it could be your iPhone or it could be Kindle client itself, right? So it's simple. You get your content from Amazon server directly over a CSP's network, right? And then, so this is the content flow, and the cost flow is that for each content you download, you also, you pay certain amount of the price of that content to Amazon, and then Amazon pays part of it to Sprint. So essentially, then Amazon's sort of revenue is going to be, not revenue, Amazon's final bottom line is going to be that whatever the cost of the content minus whatever and whichever way it had to pay the content service provider for the delivery service, right? So this actually works remarkably well because, first of all, the pricing is completely decoupled from the content as far as the consumer is concerned, because I get a book and I really don't have to worry about paying for the download price and all these things. So it really works well because of the cleanliness of the model, right? Now, obviously, the problem here is that there could be a lot of duplicated downloads if you have certain amount of locality in terms of the demand, and if you have strong community formation where the content is coming to, right? So what do I mean by that? So, it has been well understood and studied that most of the content in the net, right, it follows power law distribution. So what it means is that, you have popular objects, right, and you have unpopular objects, and the probability of request is higher for the popular objects, and the reverse is for the unpopular ones. And generally, it follows a power law, right? A power law distribution. Now, the power law distribution, the one that people have used mostly is the zip distribution, which is that probability of getting having a request for content I is inversely proportional to I raised to number alpha, which is generally zip parameter. That is generally less than 1. It has to be less than 1. Typically, 0.7, 0.8, 0.9, depending on the type of contents that we're talking about. But the bottom line is that there is a strong spatiotemporal locality in terms of the content demand that you see from the internet. And that applies to books, that applies to apps, and so on, right? So the idea is that if you have that kind of locality, then you can start thinking about alternate models for pricing, okay? So one example could be is that you have the social network, right? And then you assume, let's say, that there is a certain amount of locality. Before you get the content vertically from the Amazon server, you first do a local search. So for example, now, I want to download the New York Times page, right? The business page or let's say science page, right? So what I do is that using the near field communication, I have a community here. So I first explore this community that if I have that page, right, I get it from here. And then if I don't, then I get it from wherever the server is, right? So then the problem, as we mentioned before, is that this link cannot be free, right? Because none of you guys are going to be lending your battery power for me to get a content faster or for Amazon to save some money not paying Sprint, right? So we say that, okay, there are different types of pricing can be handled here. So one example, for instance, and it's a pretty obvious one, is that what happens is that the consumer as usually pays the cost of the book, right, to Amazon if the content was a book. And then what Amazon does is that anytime the content was delivered through a vertical link, it gives that CD amount to the content provider, the communication service provider. And then when the content is retrieved laterally, right, using an NFC, then what you do is that you give a rebate to the participants, right? It's not only you give a rebate to the guy who provided the content, right, because of its service in terms of the battery and so on, but you also give a rebate to the guy who got it to encourage that guy more and more to do lateral services, lateral searches, right? So what is the idea? The overall idea here is that if you now assume that this CR, the rebate amount, is going to be lower than the actual, the vertical download cost, then ideally, can you come up with a mechanism, right, including your network protocols, your pricing, and so on, so that at the end of the day, for a given type of content demand, Amazon's cost is going to be lower than what it used to be if it uses only exclusively vertical link, right? So mind you, this is just one example pricing. There is a whole gamut of different types of pricing that people have started thinking about, and we also have done some other work to explore different pricing. But this is a pricing model that we have done most of our analysis so far, so I'm going to stick to it at least for a while, okay? So here is the idea. So we said that this is really the key idea about trading, right? That I'm giving you my lateral bandwidth and my lateral battery, and in return I'm getting this credit. So that's the trading I'm doing, right? So depending on which stakeholder that you are looking at, the trading goal could be different, right? Somebody, if it is Amazon, it's trying to reduce the provisioning cost for each content so that its margin can be higher, right? If you're looking at the end consumer, right, its goal is going to be to minimize the energy consumption and also maybe to improve the availability, because if you have a tablet which doesn't have a vertical link, it has only lateral link, right, which is the Wi-Fi and so on. So then, or Bluetooth, then can you improve the availability for that particular end consumer and so on. So the idea is that you can have different trading goals depending on whose point of view you're looking into, right? So we will, for the next couple of slides, or in maybe a few more, we are going to look at the first goal, which is the reduce the content provider's provisioning cost, which is what I mentioned in the previous one. That you are still incentivizing nodes to pay, to give out the lateral resources, right? And while doing that, can you sort of reduce the cost for the provisioning for the content provider, right? So this is the goal that we're going to talk about here. Okay, so the next part, given in terms of time, what I'll do is that we have done quite a bit of analysis, so I'm going to just show the final expression and try to understand that, as opposed to going through the all the steps of the analysis. And all the papers that has been published is in our website, so you can always go and take a look if you're interested in more detail about the analysis part. But the problem formulation here is that what is the optimal trading policy? So you have certain network parameter, and then you have the content population, and you also know the zip parameter, in the sense that what is the power law distribution that the content popularity follows and so on, right? And you want to find the optimal content placement strategy for in a social wireless network, and then you want to minimize the provisioning cost. So right now we are going to talk about a stationary network, in a network like this where people have not moving around and so on. But we also have extended the analysis for mobile network with locality, without locality, and we're going to talk about that hopefully a little bit later. So that's really the problem formulation. So it turns out that you could come up with a fairly close from a cost expression in terms of your probability of finding the content locally within the device itself, or getting it from the network in your social wireless network, or the probability of a total miss within the network, so that you have to get it from the server. So you can compute all these different quantities, PL, PV, and so on. And the idea is that since you know the cost for each event, right, that if I get it locally versus if I get it from the network and so on, I can write an expression for cost, okay? So these are some probability computation that you have to do based on the zip distribution and so on, okay? So assuming that we can do that, and let's say that we have done this correct, then the final expression for cost looks something like this, okay? So there are two parameters that we need to look at here. One is that, so you have like three terms essentially, 1, 2, and this is the third term, right? And if you look at T here, so this T is a quantity that says that within the social network, wireless network, which is the content that has the minimum popularity within the network. Okay, so that's really is the function T. And the VC shows that what is the total storage size. V is the number of nodes in the network, and C is the storage size in each network. So therefore, V times C tells you that what is the total shared storage in the network. Okay, so these are the two quantities. T, what is the popularity of the minimum popular or the least popular object in the network, at any given point of time, and this is the storage space. So now it turns out that if I rewrite that expression for cost, there are two things that can happen. So think about the initial scenario in which what we have done is that we take the total storage space in a network and we fill them with unique objects. So in other words, there is no duplication in the network. So no two nodes in the network or no two users in the network actually have the same content that is duplicated. So everyone has unique content, right? So if you start with that situation, so there's going to be a cost, okay? So this is the cost expression for that. Then we say that, okay, now let's say that we start making some duplications, because duplication will help, because the content that are actually in the top of the popularity list, right? It makes sense to actually take those and you duplicate them in the nodes, so that, since they are going to be requested pretty frequently, it makes sense to actually have it in your cache itself, as opposed to trying to get it from the network or from the server all the time. So let's say that what you do is that you start from the first most popular node, most popular object or content, and you duplicate that, right? So the moment you do that, your cost is going to change. Now it turns out that as you do more and more duplication, the second quantity, right, that reduces, because T reduces, which is the least popular content, because you are now making more and more popular contents in the network, right? And the second quantity, that actually goes up because of this Ni times Pi, and Pi, by the way, is the probability of requesting an object, so which is, follows the zip distribution. So the idea is that the second term goes down, the third term goes up, and if you now do this iteratively, it turns out that your cost starts going down. At some point, these two effects equalizes. That is your minimum cost, and then the other one takes over, so your cost starts going up again. Okay? So this is coming purely from the analytical point of view, right? But essentially what it means is that from a physical perspective is that if you have only unique objects in the network, and then if you start duplicating only certain most popular objects from your object list, your cost starts coming down, and eventually you will find a minimum cost, at which point you will say that, okay, this is my optimal content distribution, so that the cost for the content provider is minimized while giving rebate to this participating users. Okay? And we also have proven that in fact is the optimal cost, at which point you get the minimum cost. So in this, using this equation, you get a minimum cost, and it turns out that is also an optimal cost. So I'm not going to get into the proof of the optimality. That is, again, in all the papers that we have, in some of them they actually cite give the detail of that proof. But ideally, what it means is that if you, in a static social wireless network, if you want the content provider's cost to be minimized, right, all you do is that in each node, whatever the total storage space that you have, you make them into two parts. The first part, which is lambda times C, C is the total space, and lambda is a factor less than 1. Lambda times C, number of content, you duplicate that across all nodes, okay? And then 1 minus lambda times C, you keep it unique across the entire network. And it turns out that that is the optimal policy in terms of reducing the cost. So then, you have to come up with, some amount of protocols to make sure that that can be implemented and so on. So we have implemented that. So we did simulation, and then, we compared that with our analysis that we have done, and also we have an Android prototype system, and I'm going to show one graph out of that experiment. But ideally, what it tells you is that if you assume that if you knew the popularity of the contents, and if you knew that they follow a zip distribution, if you knew the zip parameter, then you can compute the optimal lambda that is going to give you the best cost for the content provider while providing rebate to the users. Okay, so this is our cost computation. So essentially, this is the equation we have, and you derive that in terms of lambda, and you find that what is the optimal lambda for which your cost is going to be minimized. So here is how it looks. Okay, so if you look at the left graph, so I'm going to just tell the take-home messages here. In the left graph, when beta equal to 1, what that means is that, so beta is the ratio of the cost for lateral download to the cost of vertical download. So beta equal to 1 meaning that the lateral download is as expensive as getting it from the server, which is obviously not going to be practical. But it turns out if that is the case, then your lambda optimal is 1. Lambda optimal is 1 meaning that you do all duplication. And that makes sense, right? Because what happens is that since your lateral download is expensive, you might as well duplicate as many popular objects as you can in your local storage. And the other extreme is that when beta equal to 0, meaning that you don't have you have 0 lateral download cost, meaning it's free, right? So in that, meaning this is where the altruism kicks in, right? That if nobody is charging you for doing the lateral download, then your lambda opt is going to be 0. Lambda opt 0 meaning that you don't do any duplication. You keep as many unique objects as you can, right? So that your cost is going to be minimized. So now if the beta is somewhere in between, so for example, in this particular case, beta equal to 0.5 and 0.7, meaning that your lateral download cost is cheaper than vertical download, right? So Amazon is going to be paying less in terms of delivering a content. Then indeed there are points at which you will get minimum, your cost is going to be minimized, and that is going to give a specific lambda opt, meaning that now you'll be able to dimension that how much duplication you want to do in a node versus how many unique objects that you want to keep in the network. Okay, so that's really what this is talking about. So similarly now, if you start looking into the rebate part of it, right? So all these things are happening because the consumers are interested in getting the rebate. That's only when they're going to open their lateral link, right, and their storage and so on. So if you look at the graph on the right-hand side, essentially what it is showing is that the x-axis is the lateral download cost that starts from 0 and it can go up to 1, meaning the lateral download is as expensive as vertical download. So it turns out that when lambda equal to 0, then you will have monotonically increasing rebate. And that makes sense because lambda equal to 0 meaning that you don't have any duplication, which is what we are not going to use anyway. And when lambda equal to 1, that means that you have full duplication, right? So therefore, nobody is relying on someone else, and therefore your rebate is also 0 because there is no one to give the rebate to. But if you are in between, so for example, lambda equal to lambda opt, so that is the point at which Amazon, in this example, is going to be interested to set lambda equal to lambda opt because that's where its own cost is minimum. So you see what happens is that as you increase beta or as you increase the download cost, initially it goes up and then it starts going down. So this tells you that at which point, if you want to optimize the system in terms of giving most rebate out, what would be, how do you set beta so that's going to give maximum rebate out? But imagine, this is an ecosystem that you are trying to optimize based on which stakeholder is optimizing it, right? So in this case, if Amazon is trying to optimize it, it is not going to set the value of beta where it is getting the maximum rebate. It will use the cost as the primary parameter, okay, or outcome. Okay. So similarly, we have done the analysis for content density, that how the contents are distributed and so on. So this is just to understand the system a little better, so I'm going to skip that. So here, also what we have tried is that if you have a system like this, along with the protocol, and you will have popularity dynamics. So for example, Barack Obama's book came out, let's say, right? And then what is going to happen? Immediately that book, right, is going to be in the zip distribution, is going to change place. So maybe from, I don't know, maybe 10,000 popularity to it become like, popularity of 10th or second or something, right? So what you have done is that we also have looked into the dynamic, dynamical property of the protocol and the content distribution that, if you start initially during the warm-up phase, the cost has settled down, and this point you do content popularity switch and see that, how the system essentially responds to that. And it turns out, after some tweaks in the protocol and so on, it turns out, when I say tweak, I mean doing the proper design of the protocol itself. It turns out that as long as you are trying to implement that policy, optimal placement policy, and you have the right protocol to take care of that, there are some sort of difficulties I'm going to talk in the next graph in terms of implementing it. But it turns out that, the system responds reasonably well in terms of switching the popularity dynamics in the network. And this is the corresponding hit rates and so on. Okay, so as I mentioned before, so we did implement that in a prototype Android network. So initially we did it on a 7-node, and I think then it was implemented as 15-node. So I have the results for 7 nodes. So essentially, the lateral links are implemented using the Bluetooth stack of Android, and the vertical link was a Wi-Fi link that goes to a Wi-Fi access point to a server, and the server was acting as the content provider and so on. And we did implement certain amount of unreliabilities in the system and so on. So this, if you look at this graph, this shows that depending on where you are putting that, the storage factor or the duplication factor, how the provisioning cost changes. So the green one was obtained from the equation actually, and this is what we see when implemented in practice. So one of the things that came out of this, and we actually really didn't think about it before, is that the optimal policy makes a strong assumption, in fact. It makes an assumption that all requests are strictly sequential, meaning that when I send a request for an object, right, after that gets settled, then somebody else makes a request. And that's how this quote-unquote uniqueness is maintained perfectly in the network, right? But see, what happens is that if two nodes, they send requests simultaneously, right? And let's say that your server is essentially distributed. So my request goes to a server, and this request goes to another server for the same object. And even though this particular object should not be duplicated, but there is this undesirable duplication effect that happens because of this simultaneous nature of the request and also the request loss and so on, right? So in this particular test bed, it turned out that the Android Bluetooth stack, when the stack that we have used was not really reliable. Oftentimes we are losing packets and so on. So this student, he implemented AODV as the protocol there to actually go multi-hop to fetch the data and so on, the content. So because of this uniqueness issue and also the simultaneous request issue and also the loss of data and all these things, you see that there are points at which the cost is actually higher than what you would expect. But it is also clear that it is trying to follow the trend that the equations are suggesting. And we are now doing for larger network to see that how these things scale and so on. Okay. So far, what we talked about is primarily in a homogeneous network, meaning we made few assumptions. One is that the popularity distribution is exactly the same for all nodes in the network. Obviously, that's not the case, right? I mean, your request and my request is not going to be exactly identical, although it turns out that there is a substantial amount of overlap in terms of the content that is being perceived by the consumers, okay? So that is one. And second thing is that the heterogeneity in terms of the content request rate, meaning that the rate at which I download app might be different from the rate at which you download app, although we might have very similar interest in apps, right? So these are the different levels of heterogeneity that also we looked into. So one of the things that we did is that we took some existing traces that are available in terms of the web content requests. So there are a bunch of them. There is on Boston University, there is one in Saskatchewan, and then one from UCSD. So we took these traces, right? And from that, there was enough information that we could actually extract the popularity distribution for globally, meaning combining all the nodes, requests at a global level. But we were also able to look the popularity distribution for the same content on a node-by-node basis. So for example, this is the distribution for different nodes, right? And then this is the distribution when you make the aggregate of all the requests from all the nodes. So this is that. And then this is also showing that for a given object, so let's say object 18 is the blue one, right? And the green one is object 26. And if you look at the popularity of that object in different nodes, so you see that there is some amount of variation, more so for this one than this, right? So these are the types of different type of heterogeneity that you will expect if you are really trying to dimension a network like this, right? So we approached it in a similar manner as the previous one, except that now it turned out that, well, we could not actually find an optimal policy yet, right? So we tried to see that, okay, so let's see that if we can make some reasonable heuristics. So the previous one for the for the homogeneous case, it was, we had a proof that there is optimal, but we don't have one here. So we said that, okay, let's try to design a heuristic. And the heuristic that we have approached is we call a benefit-based. Now, benefit-based, the idea is that if you have a unique object in the network that is stored, right? So that is the first thing. Then what is the benefit of that? The benefit of that is that there is a benefit for the node itself, which one is storing that unique object. But there is also a benefit for other nodes in the network, because when they need that object, they can come and fetch that from me, right? So we somehow can write an expression for that, which is the first component there. Then we say that, okay, if I store a duplicated object, then what is the benefit? It turns out that if it is a duplicate, meaning everyone has it in the network, right? Then, it only benefits me, not anyone else, because everyone has it and they can just, access it locally if they need to. So this is the expression for that. So that means the combined benefit for storing an object in the network, you can, create from these two expressions. And then we say that, okay, what we'll do that anytime I fetch an object from the server, let's say Amazon server, I look at the benefit for that particular object, and then I'll compare that, the benefit of all the existing objects in my storage. And if this new benefit turns out to be higher than the previous benefit, right, the benefit of the least beneficial object, then I replace that by this object, right? So it's pretty simple. So, and then we need a bunch of protocol to make sure that's implemented and so on, but that's really, the blue text is really the goal, right? Now, it turns out that, and then we tried that benefit, okay, that benefit-based strategy, the heuristics, for homogeneous case, although it is designed for the non-homogeneous because we don't have an optimal policy for the non-homogeneous. But we tried that for homogeneous, and interestingly what happens is that it turns out that it works exactly as the optimal strategy. Okay? And we have tried that with different, wide number of different parameters, scale up, and so on. But always we found that this heuristic, in fact, does mimic the behavior of the optimal strategy for a homogeneous network, right? So this was just more like a sanity check. And then we tried to do that for the non-homogeneous, non-homogeneous, heterogeneous network. So what we did is that we took those traces from Boston University and a bunch of other places, right? And we applied to each of them and see how it performs. So if you look at, let's say this one, on the left, right? For Boston University, so actually look at the right first. So this is from this NLANR. So you have the blue one, that is the cost provided by the optimal policy for homogeneous. Then you apply this distributed benefit heuristics, that is the green one. It does improve compared to the optimal for homogeneous, right? You see the cost has come down. But we also were able to find a kind of quote-unquote lower bound. We still don't know that whether this is the ultimate lower bound, which is the black one. So essentially what we did is that we took that problem and then we mapped it to a maximum weight search in a bipartite graph and so on. And then we were able to do some integer linear programming to find a bound. Now, we think that is pretty close to the lower bound that it would be, but we are not sure yet. But nevertheless, that gives us a bound for us for both blue and the green one. And you see that by doing this benefit-based, we are able to actually reduce the cost compared to the optimal in the homogeneous case. When you apply that for the Boston University, it turns out that it is closer because that particular trace has actually less heterogeneity than the other one. So we applied that now a couple of other traces, and the findings were very similar, okay, in terms of that we are able to reduce the cost, compared to the optimal one for the homogeneous case. Okay. So the next part I'm going to talk about that now, so far we said that this thing is applied on a static network. So we have a community formation, and let's say this is my community, and all the search and everything that we talked about, the trading that happened in this static community, there is no sort of fluidity into the community, right? Okay. So if we want to now scale it up for mobility, obviously, this is just to remind that you have all sorts of interaction that is going on in a dynamic environment. People are seeing each other with different time scale and periodicity and so on, right? So the first thing that we did is that we took a case where mobility with no locality, so which is essentially a Brownian mobility, right? So what you call, let's say, random waypoint movement and so on, right? So you don't have any locality. You have a certain number of nodes. They're moving around, and they're seeing each other. So what we came up with, we thought that, okay, so let's do the following. We use the exact same policy that we have used for the optimal case, but now the network size was a parameter that we have used in our previous equations. Now the network size, we say, we use this thing called temporal partition size, or TPS. What is a temporal partition size? Which is that, if you're moving around for a certain period of time, if I see that how many unique people I have interacted for a given time frame, that is what I call is my temporal partition size for that particular duration. So obviously, if I look at it for 1 hour, my temporal partition size is going to be smaller compared to if I'm looking into the partition size for 2 hours, right? So that way, we can parameterize mobility in the following manner. We say that we call this user tolerable delay. User tolerable delay is the delay amount during which I look at the partition distribution of my network, right? So if you see that the first distribution is for a 1 second period, right? So you have your temporal partition size is more towards the smaller side, right? And then the next one is 2 minutes, right? And you see that your partition size distribution is having a pull on the right, meaning that you are seeing more and more people. And then this one is for 210 seconds. A lot of partitions are being seen of bigger size. And then finally, this one is done for 600 seconds. You see, which is 10 minutes. So you see that your partition size is mostly on this end of the spectrum, which is what you would expect, right? So the idea then is that, okay, now if I use this partition size statistics as my network size into the optimal policy and see that how that performs. So this is what we have done initially. And remember that this is without any notion of locality or periodicity in the interaction. This is completely Brownian mobility, meaning that people are moving around in a random manner in certain given area. So we use similar formulation. Okay, so here is what happens, is that if you look at the top right graph, the UTD is 1 second, meaning you say that when I want to get an Amazon book, the maximum duration that I'm ready to wait is 1 second, okay? So if I don't get it in 1 second, then I'm going to get it directly from the server, right? But maybe there are some people who are more tolerant. They say that, okay, I can wait for 10 minutes before I get the content, right? The idea here is that if your user tolerable delay is low, so that means that you will have to work with a network that is smaller because your temporal partition size is smaller as opposed to if your UTD is high, right? So for 1 second case, see, we have plotted the provisioning cost, and it turns out that you get the minimum provisioning cost when lambda equal to 1. Lambda equal to 1 meaning that if you remember that lambda is our factor of splitting, the duplicate versus unique. So lambda equal to 1 meaning all duplicate. So what that means is that if you are really impatient to get your content in this particular mobile scenario, right, then your best bet is to duplicate as many popular objects as you possibly can given your storage constraint, right? So that's what is happening here. But when you go for, in this case, let's say I'm ready to wait for 2 minutes, right? Then it turns out, see, the graphs then starts looking more and more what you have seen for the stationary case, meaning that now you have room for deciding that what kind of lambdas that you should choose in terms of minimizing your cost, okay? So the bottom line here is that this particular case, so this is the take-home message for this particular case, when we are dealing with Brownian mobility, then we are trying to apply very similar set of formulations that we have used for the static network, except that now the notion of the network size is now defined based on this number of unique nodes that you're going to see in a given period of time, which is parameterized as what we call user tolerable delay, okay? So the next thing we are going to look at is that what happens if you have interaction in locality. So this is, these are few students in my lab, and this is Mahmoud, the guy sitting here, okay? So what we did is that we used one of these Telos B type of device, right? I think this is Telos B, and then essentially we put it in a simple tag, and then we said that, okay, you guys just carry it around for a while and see that, which node sees whom, and try to get some kind of snapshot of interaction that is going on in the lab, right? So we have 6 students that has been given this badge, and also we have a fixed node, we call it locator, that is put on the lab. And we tracked this information for a while, and we took all the necessary IRBs and all these things from the university so that, university doesn't come after us. So here is an example of statistics that we, got out of it. So what is it? So we plotted contact duration between every pair of nodes and versus the number of contacts that is happening. And actually other people tried that too, and in fact, based on that, we tried to see how it looks, right? So there are a lot of interesting observations that started coming out that, how the interaction is taking place between the students. So each triangle here actually represents one pair of individual, right? So you see there are some constellations, rough constellations that are being formed, right? So if you look at the top left constellation, which says constellation number 1, student 2, right? So that shows the interaction with student 2 with other nodes, okay? And it became pretty obvious by looking at it that there is the student 2, he's a frequent short duration visitor in the lab. It turned out actually that was an undergrad student, okay? And then the other extreme, if you look at student 5, which is the constellation 3, that is rare but long duration visitor. So this guy didn't come as often, but when he came, he stayed for longer duration. And that's why that constellation is more on the contact duration higher side, but lower on the number of contacts and so on, right? So similarly, there are other observations that you could make. So why we are saying this is that there is a whole bunch of literature that is being developed in which, by using this kind of contact traces, you can do sort of graph search and things like that to find out what are the different types of communities that are being formed in the network. And our goal here is that using that community abstraction, how do you then formulate that into the optimal trading strategy that we're talking about to make sure that your objective is being met, right? Whether it's minimizing the cost or whatever it is, right? So this example. Now, there are a number of studies that has been done. In fact, these are the only 4 or 5 that I've listed here, but there's a huge number of traces that are publicly available where they give you data timestamp level so that you could do all sorts of analysis that you want to do, right? And I'll be more than happy to share with you if if you're interested in some of these links and so on, right? So there are things that have been done. So what are the different types of parameters that people have looked at to do community abstraction or community extraction? I'll just mention a couple of them. So one of them is that this INFOCOM Trace that has been done by Cambridge folks, okay? And primarily they have used similar type of characterization, the number of contact versus number of contact duration and so on, to try to understand that, that who is talking to whom, how long, and based on that, can we design sort of graph weights to find what the community is, right? So that is one approach. People also have looked into partition size. So for example, in our lab experiment, this is the average in the steady state. This is the distribution of the partition size for each node in the network. So now you know that which node. So for example, if you look at the locator is a static node, right? So its partition size is kind of uniformly distributed. Whereas if you look at student 2, it is the partition size is 1, meaning that most of the times it had that student has a one-on-one type of interaction as opposed to being on a group, and that was an undergrad student working with a graduate student. So things of that nature. So similarly, from the INFOCOM Trace, there is also you could do partition distribution data, not only static, but you can also look at what is the dynamics of partition distribution, so that you can use that to find your community structures. The other thing also people have looked into, which is called node degree and centrality. Okay, so node degree is the standard node degree in a graph, right? That how many nodes you are connected to. But centrality is that it says, in a high level, centrality is that how important you are in terms of bridging between two different communities that would not have visiting each other. Okay, so having a high nodal degree doesn't necessarily mean that you are a central, a central member in a society, right? In terms of bridging between two communities, and so on. So people have looked at this type of centrality versus centrality type of indices also to figure out that how do you do community abstraction. And there is nothing written in stone. There is a lot of work that is going on, and people tried from different angles to see that what community formation algorithm makes sense for what kind of applications. Okay, so this is really what this particular view graph shows you. That so this is my just a refresher. This was my LinkedIn profile, right? Not profile, the graph, right? Now you can apply. There is this whole host of different types of mechanisms, which are being written around the periphery to extract different types of community that is there in that graph, right? So similarly, for a social wireless network, you will also have a graph like that. The only thing is going to be more dynamic because of mobility and so on. And then you can apply this type of algorithms to extract your community. So there is one that generally people use quite often, more than the other, is this K-Clique community extraction algorithm. So it's a pretty well-established mechanism. Basically, it says that you have a clique in a graph. A clique is essentially you have a fully connected subgraph within a graph. That is a clique, right? And then you define a K-Clique. Essentially, what it says is that a K-Clique community. So this is a 4 overlapping 4-clique community. The idea is that you will have in a K-Clique community, you will have cliques of size k. They are connected to each other, and they will share two adjacent cliques will share k-1 nodes to get interconnected between them. So let's not get into the detail, but the idea is that now by adjusting the parameter k, right, you can say that I want to detect more number of communities versus less number of communities, or what is the degree of cohesion between these two communities. Okay, so think about this, the thing that we did, the experiment that you have done in our lab. Now, if I can characterize the link between every member within a community by certain parameter, let's say contact frequency is the parameter, right? Then I can apply things of this nature to say that where the community boundaries are and how these communities are connected and how they're overlapped, right? So once I do that, then I'll be able to apply some of the previous principles that you have developed and show that we can do better trading in terms of the objective that you are targeting to. So one of the things that we have done is that you use, let's say, K-Clique. Doesn't have to be K-Clique. Use your most favorite one. And then you do the community extraction. Then you use that community size parameter into your cost formulation that we have done, right? And then one of the things that we tried is that you do this hierarchical splitting. You say that the total storage that I have, now I have 3 parts. One is duplicate part. That is only for me to get content locally. And then I have one part which is unique in the community, because I know now, using this community formation algorithms, I know that who my community members are. So within that community, I make sure that this thing is unique within that community. And then there is another part which is unique in the network. Okay, so now instead of just lambda, we have 2 parameters, which is lambda and mu. And this is done on a per node basis, remember, because everybody's mobility pattern is different, right? So the idea is that then you try to see that how this performs. So we have, we don't have a nice mathematical formulation for this yet. So far, what we have tried is mostly experiments through simulation to see that, how this works. So one of the students is actually looking into trying to develop a better math for it. So So here is one trace from INFOCOM that is published by the Cambridge folks that we have taken the trace and then applied the hierarchical content placement policy that we talked about. So this is the cost. And this shows the comparison between if you had done hierarchical versus non-hierarchical, meaning that let's say that you are completely oblivious to this community formation. What you do is that you apply it in a flat manner, like what we have done before the community formation and take the ratio of these two and shows that how well the hierarchical split that works. So it turns out that it does reasonably well so far, but as I said, that we don't have an optimality, we don't even have a proper formulation yet. So this is so far mostly on experimental evidence that by doing hierarchical storage in that manner is most likely to help. Okay, so we have tried that for other traces that are available, 3 or 4 different traces. So the last topic, I'm going to take probably 2 minutes to summarize some of the concepts. So one of the things that that how do you really enforce these things, right? I mean, this is always a case, right? And especially when you are dealing with a peer-to-peer system, enforcement is always a problem, right? So one solution might happen in the following way. You say that, okay, if Amazon is going to implement that, you download the Kindle app, and Kindle app has all these policies embedded in it, right? So based on the community measurements that Amazon is doing on the side, and they always, already they do that, those kind of stuff, they can periodically send that data to your Kindle app, and the app computes those lambdas and mu's based on these parameters it is getting, and that way the user really does not have an option to be selfish. So why would you be selfish? Selfish is obvious, that I get a micro rebate for providing my service, right? So one of the things that I could do easily is that I could choose a lambda, which is the duplication versus unique boundary, which is not optimal. I say that I choose a lambda s as opposed to lambda opt, and I choose lambda s in a way so that I store a lot of duplicate objects. So I give it to duplicate or unique objects, I give it to people, I earn a lot of money, right, through rebate. But at the end of the day, the overall network cost is no longer going to be minimum, which is what Amazon is trying to do, right? So there are different types of selfishness that can be attempted in a network like this. So one of the things that we did is that we chose one type of selfishness, which is that a node uses lambda s, which is a selfish parameter for lambda, as opposed to lambda opt, which is what you would do if you are a good guy, right? So we did, manage to compute the cost for it, and this turned out to be pretty close from. So here's what, is probably my last but one slide. So here's what one of the things that it turned out. So there are 2 interesting observations. So the first observation is that if I plot lambda s, which is the selfish split point, right? It turns out that when lambda s is same as lambda opt, so there are 2 cases. One is for beta equal to 0.5. Beta is related to the lateral download cost. So one for 0.5 and one for 0.9. So 0.5 has a lower lateral download cost, okay? So let's take out the red line, okay? So what happens is that when lambda s is the same as lambda opt, which is 0.2 something, then you see that the earned rebate becomes same for the non-selfish node, which is the red dotted line, and also the selfish node, which is the thick squares, right? But beyond that, in both ways, the selfish node actually can manage to earn more rebate, and that's what the equations were for. They can earn more rebate compared to the, and the same thing is also for the green line, which is for a higher lateral download cost, right? But the interesting observation here is that if a node is working without collusion, meaning that if a node is working just by itself in terms of being selfish, it makes sense for it either to choose lambda s to be 0 or lambda s to be 1 to maximize its benefit, okay? Meaning that you either duplicate as many objects as you can, or you don't do any duplicate. And it turns out these are the only 2 cases where you can maximize your rebate, okay? And that's what is coming from the equation there, okay? So this is one observation. Second observation is that if I look at, so just ignore all the clutter, let's look at only the top right graph. So what this shows is that now each node is acting on its own. It doesn't know that it's not colluding. So it is using a policy almost as though it's acting on its own, right? So it's going to be choosing lambda s to be either 0 or 1, depending on which one is going to maximize its goal. And that can be found out from the previous equation. So now, if I plot the number of selfish nodes in the network, so this particular case there are 40 nodes. So 0 meaning no selfish node, that is the, everyone is going by the protocol, and then 40 is where all nodes are selfish, right? And then I plot the earned rebate per request. So the interesting thing is that the green one is a selfish. Obviously, it has a higher rebate initially, but once the number of nodes, selfish nodes, reach a critical value, which is looked at, shown as lambda critical, there is this point of inflection beyond which actually their per node rebate goes down compared to the non-selfish one. And the reason for this is that then what happens is that they have grown, the population of selfish nodes grown so much that per node rebate is no longer paying them the cost of being selfish, because then the non-selfish nodes actually starts providing content to the selfish nodes, right? And they are getting more rebate, which is the blue line. And this trend turns out to be true even when the value of beta, meaning the cost of lateral download, is different. So that's what we see here, that when beta equal to 0.5 and the other values too, if you look at the same graph on the right, that there is an inflection point. In fact, in this case, that crossover point is in fact earlier. So the bottom line here is that this is not understood. We haven't worked on it yet, and I think that's where there is room for doing some game theory analysis. That the selfishness, you cannot be blindly selfish. You might be thinking that I'm getting a lot more rebate than the others, but in fact it is not true. If there are other nodes trying to be also selfish, there is this point beyond which it really doesn't pay to be selfish. In fact, it hurts you, right? So how do you find the strategy being a selfish user? And obviously then the next question is that what strategy you will put from the content provider's point of view to make sure that try to be over selfish even in the presence of collusion is not going to pay you what you want, right? So I think I'm going to essentially wrap up my presentation here with maybe 2 slides just to give you some thoughts that where this thing is going. So one thing is that more like a strategy and the marketplace, right? So the idea is that this open ecosystem for supporting new business and pricing models, right? Now, the interesting thing for us as university researchers, right, that you can make this leap of assumptions and say that, okay, I'm going to assume that the marketplace is going to evolve this way, and this way, with this kind of pricing arrangement and so on. And in each of these scenarios, how the technology is going to be developed, right, both in terms of protocols and and so on, to make sure that these kind of things could be implemented. And if you see already, if you're aware of what is going on in the app market and on the mobile ad market, right, there is a significant amount of innovative thinking that is going on in terms of this different type of pricing arrangement, dependencies, ecosystem evolution, and so on, right? Because as you know, that Google's and Amazon's and Apple, right, they're building their ecosystem. If you have a Google tablet, Android tablet, right, everything is Google there. So they want you to spend as much time as possible on the ecosystem so that they get all your profiles, your communities, and so on, and they want to push you stuff what they can make money out of, right? So in that process, there's going to be a huge amount of new thinking in terms of this dependence, in terms of pricing, not necessarily just in technology. That's going to be shaping this line of research that we are talking about here, right? Then there is a lot of auction-based work that people started talking about, right? So I'll give you an example. In Google's, when you do a Google search, right, you see that when you do a search, on the right you see that there are these ads that show up, right? Now, I don't know whether you are aware of that or not, that there is a runtime auction that goes on when those ads show up, in the sense that there are only limited places, right? Only, let's say, 10 places in your first page, and that's the premium place, right? So there are always at least 100 or more ad pushers that are lining up to get these 10 places, right? So what they do is that when you are doing your search, they run actually runtime auctioning on the background, and the guys who win, they show up on those 10 premium places, right? So there is a huge amount of work that can also be done, and people started thinking about to take that concept, right, and then blend into this physical social network that we talked about, or mobile network we talked about. So these are things that needs to be thought through. And then if you're talking about trading bandwidth, obviously this spectrum, license spectrum, cognitive radio thing, people have started solving the technology part of it, but how that's going to show up in the big picture as a jigsaw puzzle in the whole trading atmosphere, right? That has not been understood well yet, right? Then third-party involvement in terms of who is going to manage those incentives, right? So if a third party wants to manage the incentive, how do you then sort of be more creative in terms of pricing, what technological advances that is needed? So those are the things that is going to be worth thinking about. And then there is a huge set of different sort of technology issues that also needs to be looked at. I mentioned a few of them already. So right now, there are 2 areas that we are working pretty actively. The top right one is the economy-driven Xcast, this is multicast or whatever you call it, right? The idea is that if you want to push content in an ecosystem, right, then how do you incentivize people to actually help you have better penetration into the community so that you can maximize the margin for whoever is trying to push it, right? So it's a fairly interesting network routing / medium access control type of problem, but now you approach the problem more from an economy perspective rather than the traditional objectives that you want to minimize, right? So that's one. There's the other thing that we started talking about. One of the things that I started talking to Shumit for a while now, that when you are trying to do this download, right? So far we are saying that the download from the vertical link is really a standalone process, right? But it doesn't have to be. If there are multiple nodes that are interested in the same content, then what kind of shared downloading mechanisms that you can think about that's going to add to your cost bottom line. So those are the kind of things also needs to be thought through. So with that, I'll stop my presentation here. Sorry for being a little over time. A huge number of papers that has been published, and we got some best paper award and whatnot from this work that we have. So if you care to learn a little bit more, just go there, and papers are all listed there, and feel free to send me an email. I'll be more than happy to help you out whatever I can, or hook you up with my students, and that's where it stops. Thank you.
Since we're over time, any quick questions? Okay. Well, he'll be around if any of you want to meet with him, so let's thank him again.